is also L2, L1, and here the distance between them is D1, and here it is I'll try to use maximum colors as possible because so that you can just read it properly. And you asked to find the capacitance in between them, right? So we draw the side view, and I specifically instruct the grader that he will be giving you grade for the sketch, even if your answers are wrong. Okay, just make sure that in exam you just make sure that you just draw all the sketches. Okay, so these are the dimensions given in the problem. You will not be given any more details. Okay, so this was the L2, right? And L1 I cannot draw because I'm just looking at 2 dimension, just from the side. Okay, so what we did, we just assumed. So the problem here is that the capacitance is not unique, right? If I take a strip or this piece of this one, even though that piece have some misalignment, right? So I cannot just say continue to small pieces and do it, right? It's a continuously just changing the height or the distance. So I assume a small portion of it having a small capacitance, DC, right? And that small portion have a small area, right? So that small area is dA, right? And also, I wanted to know how the capacitance is changing over the distance I'm moving on the length. So I just assume that this is the capacitance, the small capacitance I took at a distance of x from the one edge. You can take from the anywhere. Okay, so this small distance on the x-axis will be dx. Right? So when you look at the 2-dimensional picture, right, of a single plate, you see that small DC is very small, right? It's unrecognizable, but for sake of the schematic, I just draw some area here, and I have area dA, right? And I have here L1 and here L2, and this length is dx. Correct? So what would be the area on this small section? What would be my dA? L1 into dx, right? If you take this length dx and this total length is L1, right? So you have L1 into dx. This is clear, right? And we already know the capacitance of a parallel plate capacitor, epsilon 0, area over distance. Capacitance doesn't depend on the charge or the potential. Okay. So for a small capacitance, this is a general equation. This is a general when you have a parallel plate capacitor. But in this case, when you have a small capacitance, let's say C is equal to epsilon 0, and I'm talking about a capacitance on the small area, right? So this is a dA, right? Some distance which is changing as a function of x, right? So now,
Would that be DC?
this one?
Yeah, is it DC?
Oh, sorry, this is DC. Yep, you're right. Small capacitance. Thanks. Okay. So I assume that I have a small capacitance over an area of dA, right? And if I take the capacitance from here to here as a continuous function, I can get all over the small capacitance, right? And if I integrate from here to here, I can find the whole capacitance. That's the idea, right? So the distance function, I mean, in the example I was given y of x because typically we take y and x. You can take any function. But it's just changing, since you consider this as a x, so it's changing as a function of x. And we assume that initially I have the distance, this point, d1, right? When x is equal to 0, y of 0 is d1. When x is equal to L2, right? So this is the L2. L2 is the total length, right? So this is 0, this is L2. And now when x is equal to L2, my y of x is d2. So I have to get a function such that initially it should be only d1 and finally it should be d2, right? And in between, I keep changing, it should increase the height between the capacitors, right? So maybe I'll use another color. So, how much the height is changing? This is d2 minus d1, right? So my height d2 minus d1 is changing as a function of x. So you can just write the function y of x is equal to d1 initially plus d2 minus d1, right? As a function of x, right? So just look at this. When x is equal to 0, this whole term will be 0. I only have d1, right? When x is equal to L2, what happened? d1 plus d2 minus d1 L2. So that I will get this one. Just check when x is equal to 0, my y of x will be equal to d1 plus d2 minus d1 to 0, what about that? That will be d1. And when is equal to x is equal to L2, when x is equal to L2, my y of x will be d1 plus d2 minus d1 into L2 over L2. So this
The
will be,
equation you gave us last week was different.
sorry,
The equation you gave us last week didn't have L2 in it.
what was the difference?
There was no like divide by L2.
Did I miss that?
Yes.
Last time? Okay, so this is the right one. So check this one. So d1 plus d2 minus d1. This will be d2, right? Did I give you equation last time? I just told you to solve it.
You
You
told
said-
it-
You
you
gave us
told
the
it as a
L point and you
function
said
of x.
continue it.
As a function of x.
Yeah, so it was missing out the L2, so the final answer is no.
Okay, that's why those things were. I thought I didn't give you any solution for this.
You gave us up until about.
Okay, maybe then I missed it, this part.
Yeah.
This is the correct form, okay? Just check it. So this is how that function should behave. Okay, just forget about the solution you provide. This is the right solution. I think that's why I found all the solutions. Some of them, I mean, I think a couple of people did, right? Yeah. Yeah, some of them have unimaginable solutions. Okay, so function of something. Okay, then now this is how you. So I really wanted to explain this part because you should know how these functions are coming. I can just write, okay, y is a function of this one, this equation. It doesn't make any sense unless it just changes as a function of x, and you have to see how it is changing. Okay. Now we have the capacitance epsilon 0, then the small capacitance, epsilon 0 dA over y of x, which is the distance as a function of x. So this will be epsilon 0, and what was our dA?
L1 dx.
L1 dx over, what is our y of x? D1 plus d2 minus d1
X by L2.
x by, this is my DC, the small capacitor, right? Now, from where to where I have integrated?
0 to 1.
This is my whole capacitors, right? So I have a small capacitor, infinitely small capacitors here, from going from 0 to L2. So if I want to find the total capacitance, should be 0 to L2 epsilon 0 L1 dx over d1 plus d2 minus d1 x over L2. This is correct, right? Just check it. Now, you can take the constants outside, epsilon 0 L1 over, maybe you can multiply this L2 with d1, so, and you can take the L2 out of the bracket.
What is that? Can you consider D2 minus D1 over L2 is just like a constant?
You can do that. Or you can just take this one, so that we just take all the stuff outside, right?
Professor, but if you distribute the as a denominator, it's going to have an x, so you're going to have to keep it inside to integrate it.
This one?
Yeah.
You can do it multiple ways, right? So, you can just directly just take this outside as a constant, and you have a dx and a function of x, right? And you can just take whole things as u or something, some substitution, okay? And then you can do it. The easiest way is that you just multiply this with this one, so that you have L2 over all over L2, right? Then when you take it out, it just 1 over L2 here, right? So it will just go up here. Clear? You want me to write all the steps, or this is okay, right? So this will be, sorry, this is 0 to L2 dx over d1 L2 plus d2 minus d1 into x, right? The reason I just do that, because I just wanted to make sure that I don't have a lot of term along with the x. Otherwise, I have to repeatedly writing the L2. So I just multiply this one, whole things, not whole things, this one with L2, and then just divide with that, and I can take L2 here. So this would be here. So this is 1 over L2. Right? So now, how I solve this integration?
Take the denominator as u.
So this one you just use the substitution method, right? So you substitute this as u, right? So this you can write u is equal
Professor,
to,
just separate the integral to make solving it easier.
you can just do that, but you can either just take this term and do that, right? I just choose one method. It doesn't matter whichever method you do, you will get the same answer. Okay?
How can you separate the integral if it's an addition in the denominator?
That you cannot do. You can choose any other method if you know any other method. I'll just use this one. This is the easiest one, and this is the one you just learn in calculus when you have a function which is coming with some constants. Okay? So substitution method is a method you typically use when you have a function with some constant.
But separating it is a long process.
d1 L2 plus d2 minus d1 into x. And what is the differentiation of this one?
d2 minus d1 dx.
d2 minus d1 dx, right? And what are the limits? Just remember this, in your exams, I have seen that you solve the problem. You know how to do the substitution. But you miss this part. When you change, you substitute with something, right? So your limit will change depending upon the substitution. So what is the limit? When I have x is equal to 0, what is u?
D1 and 2.
d1 L2, right?
Yeah.
d1 L2. When I have x is equal to 0. When I have x is equal to L2, what is the limit?
D2. D2 and 2. Because D1 and
So
2.
d1 L2 and d2 minus d1 L2, right?
Yeah.
So d1 L2 and minus d1 L2 will be cancelled out. So I have D2 into L2. Instead of X, I substitute this one. So B2, L2. So now you just do the integration. So this will be epsilon 0, L1, L2. Instead of 0, you have D1, L2, right? Instead of L2, you have B2, L2. And what is dx? du over
D2 minus
dx is equal to du over d2 minus dx, right? So d2 minus d1. And you know, 1 over. Now you can integrate this one. And what will be the answer for this one?
Log
Sorry?
and
Yeah, 1 over u du. Integral will be log of whatever the limits, right? So you have c is equal to epsilon 0 L1 L2 over d2 minus d1, right? You can just have ln of a with the limit d1 L2 d2 L2, right? So this will be epsilon 0 L1 L2 d2 minus d1. And what is this one? ln of d2 L2, right? Minus ln of, I'm writing all the steps, ln of d1 L2, right? So this I can write epsilon 0 L1 L2 d2 minus d1 ln of d2 L2 over d1 L2, right? So this can be cancelled out, right? So the answer will be c is equal to epsilon 0 L1 L2 d2 minus d1 ln of d2 over d1. Okay. This is correct. Any mistakes or any steps you want to understand?
Sir, when we take the problem, like when we angle one of the parallel plate capacitors,
Yeah.
it doesn't reach till the like end of the bottom one, right?
Ideally, it should not, because when you have something at the same height, same length, when you just change this one, right? So you will not have. It's a good question. You will not have. For example, I have something like 1 meter plate here, right? And then I have another 1 meter plate here. This is my parallel plate capacity. Now, in this question, what I did, I just changing 1 meter, for example, for an extreme case, I just change this one to 1. So you will not have capacitance. So, but you will have a total capacitance like this. Okay. So yeah. So that is why you have the capacitance function going as a log of the distance between them. Now, this is clear. Any question from this one? This question is very, very good. But I'll be asking similar questions for you. That's why I just called it. And I'll be, from this chapter, I'll be having a couple of more questions. Now, after this, we discuss about the dielectrics, right? So how I can increase the capacitance of a capacitor? Because when you want to store more charges, you need to have the more capacitance, right? Ideally, you should have a more area or less separation between them. Like I briefly discussed this in the last class. So I'll just repeat it. Because these things are really important. For example, so I have a capacitor, right? We'll take a simple example. I have a parallel capacitor. I have some length and so let's say, so this is L, this is L, some or L1, L2, L2, L1, and I can find some area, right? So my capacitance depends on epsilon 0 area over this suppression, right? If I want to increase the capacitance, what should I increase? If I increase the distance, whether the capacitance will decrease. So what happens if I decrease the distance between them? The capacitance can be increased, but I cannot store a lot of charges because, as you know, when you have a very close plate and you apply huge potential between them, there will be electric breakdown, right? If you have a perfect vacuum, you can only go up to something like 1000 volt DC in between two plates. That's a typical number. So you have to you have to keep a separation of something like minimum. If you want to apply something like 1000 volt in vacuum, you have to keep a minimum of 1 millimeter, right? So in ambient pressure, we have a lot of nitrogen, we have a lot of gases. So when you just keep this potential, as I said in the last class, you keep some atoms or any kind of atoms in between a huge potential, right? The electrons will try to move away from the negative, and the nucleus will try to go this way, right? And if you keep increasing these potentials, after a certain time, this electron will leave, and this will get ionized. That is how the plasma creates. That's how when you have the lightning happens, you see the lights coming, right? So the lightning light is just ionizing the air in between the cloud and the ground, right? So this happens. So you cannot just simply just decrease this one and increase this one. There's a limit to this one. The other thing you can do, just increase this one, right? And just keep this one constant, but you have a limit to increase the capacitors, right? If you open a capacitor, you see that the plates are folded, right? You see typically, there are different kinds of capacitors. The ceramic capacitor you see are having a shape of, typically this shape, right? But you see other kind of capacitors, these are cylindrical capacitors, right? Typically these capacitors are in microfarad, and this is a bit higher capacity. The reason you have this one is that they want to increase the area, so that if you increase the area, the capacitance can be increased. But here in this case, you cannot have, you have a limited area. For small applications, we typically use the ceramic capacitors. But for the higher charge applications, we use the cylindrical capacitors. But there are different ways to solve this problem. That is where the dielectric comes, right? So we discussed this in the last class. I'll just briefly go through this. So, as I mentioned, you take a capacitor, right? And you charge them so that we have one plate will be positive, another will be negative when you apply some potential. And if you keep an atom, for example, a neutral hydrogen atom, and the most classical picture of the hydrogen atom is, even though this is not a real atomic picture, whatever we learned, you have a nucleus and you have an electron revolving. In reality, you don't have such system. You have a nucleus, and few kilometers away you have, if you consider the scale of this one, because one is in 10 power minus 15, one is 10 power minus 12. So you have electron clouds, right? So let's assume it, just go with the Bohr's model, where we have a nucleus at the center, and we have electron revolving around, right? And I keep some potential difference between these two. What happens if I keep increasing the potential? Even though this is a neutral atom, right? This will feel some potential, right? Because when I have potential, I will definitely have electric field, right? Right? I will have, when I have potential, I will have electric field. So this electric field causes the atom to get distorted in a way that this positive side of the atom, right, will go this side, and negative side will be coming this side. They still hold together if I am not applying so much voltage. If I am applying the ionization voltage more than the ionization voltage of hydrogen, what is the ionization voltage of hydrogen? How much energy you need to kick out an electron from a hydrogen atom? Something like 13.6 eV. Just for example. So if you are not applying such amount of potential or the energy, this will be still an hydrogen atom. But the negative side will just push this way, and the positive side will push that way. So this will form a kind of a dipole, right? So they are separated with a distance, let's say distance b, you can define a dipole. Okay? So people use this idea to increase the capacities. What they did, they took certain material. The best material to create a more capacity is the water, but we don't use it because of conductor. And okay, this is a case when you have a neutral atom which doesn't have a conductor. If I keep a conductor in between, this one here, or just some element I keep as a conductor, I will no more hold the potential difference, right? Because the charges will flow from here to there, so continuously. So I hold this one, the potential between these plates. And I insert some non-conducting material, right? If you use a deionized water or distilled water, it's a non-conducting material, but normal water, the tap water is conduct. So that's why you just put electricity in a water, and if you touch it, you get it. So water or silicon or anything else. Such a way that the atoms has to be oriented in such a way that the lattice should be having some pattern like this, some regular pattern. So which means each atom, the positive and negative like this. So if I keep this going, the potential increasing, so the positive charge will from and each atom will go this way, and negative will just come this side, right? So this will keep going. And this is a non-conducting material by the way. It's not conductor. If it is a conductor, doesn't matter, you just apply some voltage, the charges will flow through it, right? So it will be like this. And what happened to the edges? If you look at this one, these edges, you have negative charge here, right? You have positive charge here, right? So, and also you have an electric field due to the plates here. And that electric field is making this distortion in the atom. So all the electric fields are going this way due to this potential. So from positive to negative, right? So if you look at the electric field inside, this will be something distorted. Because the electric field, whatever here, if you don't have any material, this will be equal to whatever the electric field go in this direction, right? Obvious. But when you look at this one, this electric field will be distorted due to the charge differences in this atom. So the inside electric field, effective inside electric field will be less than the outside electric field. And by using only one of these technique, you can increase the capacities depending upon how much charges you can fit into these things. For example, here I took only 5-6 charges. If I take a dense metal or material, or not a metal, a non-conductor, and if I can fit this dense material inside these two plates and keep applying the voltages, and dense means more number of atoms, right? So I can get more capacitance. So the capacity, what is the capacitance? Charge over potential, right? So what is the potential? Electric field into distance, right? So when you increase the or decrease the electric field, when you decrease this one, what happened? This will go up, right? That is what we do when we are inserting a material inside a capacitor, right? And these kind of materials are called dielectric material. Okay? So when you look at the capacitance inside and outside, you see a differences. Or when you look at the capacitance in this region, or where the region you don't have any charges, you will see, let's say that capacitance 0 or capacitance out will be higher than whatever the capacitance inside. You can call this as inside. Because the inside capacitance will be going Q over E inside, right, into D, and the outside capacitors or whatever you have, you don't have any material, it will be going D. And if you compare this one, so this will be C inside will be much more than C outside. Because this goes as 1 over E inside, right? And this is also goes as 1 over E inside. So if you decrease this one, you can have more number. If you decrease, I mean, you cannot decrease this one, this will be constant one. You are doing it, not nothing to this one. So, as many as atom you can pack in between a capacitor, that increases the capacitance times of whatever the electric field is. So that's the idea, okay? And this constant is called dielectric constant. So typically when you open a capacitor, especially the ceramic capacitors, as I mentioned, we will be using for small capacitance applications. So mostly, even though we use the dielectrics in a ceramic capacitance, right? We in all type of capacitance we use the dielectric. But when you open the ceramic one, you will not be seeing the dielectric material inside, because that's a very small one. But when you open these kind of capacitors, these kind of capacitors, if you see, they have a aluminum shielding outside with some cover. If you tear it off, you can just open it and you see some long sheet which was folded into here. Typically they use a silicon sheet or gallium arsenide sheet or something, okay? And silicon will just give you this capacitance of something like, the dielectric constant is something like 15 or something. You don't need to know that, because I'll not be asking some numerical questions like this, okay? But if you use a perfect water without any ionization, I mean, you can of course have tap water, but the problem is that if you keep tap water between two potential, you will get the charge flowing through it, right? Like that's why some of the accidents happens when you accidentally in a river or something, you just if you high voltage or high tension wires broken down and just touch on the river or something, if somebody is just touching that water, they will get the shock, because the water will just transmit the electricity. Okay. Same as our body. Our body is made up of lot of blood streams, right? So if you use a deionized water, distilled water, you can just keep this potential difference. And now you will not have a direct question from this, but you will have a question from this. I take a material and just fill it half of the capacitors, for example, into that material. And what will be the total capacitance? For example, a parallel plate capacitor separated with a distance of d. is half filled with a dielectric material of K is the dielectric constant of that. Okay? Find the total capacitance of the system. Right? So, first thing first, you have the capacitor. A capacitor of length L. Just a second. So you have a parallel capacitor. Let's say that they are a square capacitor so that I don't need to write. Right? And they are separated with a distance of d. If you look at the this is it. And now I fill this one from half part from material. If you look at from this one, I just fill this one. This one, dielectric constant. Find the capacitors. Total charge is K.
Is it series or parallel?
Sorry?
Is it series or parallel?
This is, I took a parallel capacitor, a single capacitor, right? And I just insert some material where it fills halfway through. So you should calculate the total capacitance of this. I will do this one. You can just assume the area is L square or just take that the total area as A and just half of the part is A by 2 or you can assume anything. Solve it. You know the equation for the parallel capacitor, you know the equation for the dielectric constant. So when you have a dielectric constant in a capacitor, so the capacitance will be the constant into epsilon 0 A over B. Okay? Right, solve it. So whenever you get a question for a capacitors, I told you just write the equivalence capacitors, right? So you can split that into two. See, so this is a single capacitor, right? So you can just split them let's say this is C1 and this is C2 and this is a capacitor which is having the dielectric material. This is a capacitor which doesn't have the dielectric material. Now what is this connection called? Is it parallel or series connection? Parallel or series?
Parallel.
Parallel. Series? It's a parallel connection. Series is just, it's a series. repeating this way, okay? Just remember that. When you have a parallel capacitance, the total capacitance will be this one, right? So just add this. And the area you can just take L by 2 this way, or you just take the area, total area is A, then L by 2, right? I don't care. So what is the answer for this one?
It would be epsilon into L squared by 2 over D plus
Epsilon into L squared
by 2,
by 2.
L squared by 2.
So
Like,
the area.
it's L by 2 into L.
Okay, then
Not whole squared, the L is squared.
L squared over 2.
Yeah.
Here, okay, then
Over D
over D.
plus K.
Plus should be here, right?
K into this one.
0, 0, L squared over 2 over D. So this is C1 and this is C2, right? And what will be the resultant things? Epsilon 0, L squared over 2 D 1 plus K. You can write like this, right? I just took the constants L square over 2 and just epsilon 0 L square over 2, both of them. Those are the common things, right? So I just took out. And now, what happens when when I remove the, I just remove the dielectric material from this capacitor? It will be epsilon 0 L square over D. This is the area, right? And this is the distance, right? So when you have a capacitor, you have the area is L squared, right? A simple capacitor. And you just add a dielectric material halfway through it, and when you solve it, you just split them into two, right? So again, if you remove those parts, this will come to the original results, right? It should be.
Professor,
Yeah.
was it specified that they're squares?
This one?
Yeah, with equal dimensions, because you wrote it as L squared.
I just mentioned here they have the L the equal dimension. So the area should be L squared. So this into this, right? So
I thought they were rectangles.
no. If it is L1 and L2, you can write it. But I just wanted to make sure that for the next proof. Okay? I just wanted to make sure that they are equal. Okay, now this understood? This is simply I just took a capacitor, right? With an area of A, which is L squared, because I have the side L and another side here. So I can find the capacitance here L square over D if this is the expression, right? This is the original capacitor. Now I insert a material with some dielectric constant. Now I got the capacitance in this form, right? Then if I remove that part, then I'll get this same result. Okay? So confusing? No?
That's the last part, is that when you remove what? Oh.
I'll repeat this one. Because this is very important for the next problem. So this is very simple one. So you take a capacitor, a parallel plate capacitor separated with a distance d, right? You take it, and you have a capacitance of epsilon. If it is the lengths are L, the area is L square over D, right? The capacitance is epsilon 0 A over D, right? And my area is L square. Now, if I fill half part of that, when I solve, because of these two sides have different capacitance, I can split them into two, and I solve it, right? Now I'm saying, in case if I just remove the capacitance, I have to get the original one, right? Which means my K should be 1 then. So if my K is 1, so this will be epsilon 0 L squared 2 over 2D, right? 2 cancels. So I'll get epsilon 0 L square over D. This is clear. Now, I have another question. I just took a capacitor of same type, and now now I took, this is the next question, okay? I took a capacitor. These are positively charged on plate. Same as the previous one, and negatively charged on the one side. Okay? Now, I take a dielectric material from somewhere, same side. And I just try to keep this one here. Try to insert this one. Okay? So whenever I have a dielectric material in between these two plates, definitely I will have negative charge from the edges on this one, right? Like we see the dipoles form. And this one will be, I'll use it. This is really, really interesting. So I have the negative charge on one side and positive charge from the dielectric material on another side, right? So when I start to insert through a plate, it will experience a force, right? An electrostatic force. So that force will be depending upon the energy available here, right? So you know the force equation, right? So find the force. I'm not done with the question. So the sketch I just draw to make you understand. So I'll write the question. If you understood that part, this will be a little bit easier. Find the force acting on the dielectric. I'll call them a slab or just a piece of dielectric. Inserting on the parallel plate capacitor of dimension. When I say dimension L, I mean the width. In some of the question, I will not be specifying. Width is equal to L and length is equal to L. So both of them are same, right? So I have this one. So L and L. So I have another capacitor here. So which are also same L and L. And I'm inserting some slab of material. Right. So which means this piece of I will be asking you capacitor I'll be asking to find the force. Find the force at the capacitor dimension L separated with a or separated by D. This statement is clear? It's clear? So find the, so I have the parallel plate capacitor of length L, right? And I take a piece of dielectric slab and just try to insert it. Since I have the potential difference here, and there the dielectric material will feel the charges at the edge of this one, so there will be force. So find the force actually. So how do you find the force? So when you have a capacitor, what is the equation for the energy? Half CV square in terms of potential, but in terms of charge. So you can just U of X is equal to half Q square over C, right? So you first find the capacitance, right? then use the u of x with that capacitance, right? So then if you want to find the force, find dou u of x over x. Can you do this? Or you want me to do? Want me to do this? So, what is the capacitance here? So, the same way as you split that part, you can split this into two capacitors, right? So, let's say you have the total length is L, right? Right? And you are keeping inserting this one. Okay? So the insertion point is changing, right? So let's assume this distance is x. You can assume any letter. I'm just choosing for sake of the convenience. This x is typically used. So you can just choose this as x, right? Now, what will be the, if you split these two capacitors, what will be the area of the first one? So I split this part. Okay, I just split them into, but I have the direct material which is having some capacitance. So let's say C1 and C2. So what is the area of the C1?
Squared by 2.
It's not L square by 2.
And x.
The length is L,
L to x.
right? And for the width is L. So you have now the plates like this, right? So I just insert something halfway through it, right? But this L doesn't change. This L changes to, this is my total L, right? So this changes to, if it is not halfway through, just somewhere.
L minus x.
So that would be L minus x, right? So L into, for the first part, this part,
It's alex.
this is x. And for the second one, let's talk only about area. The area of the second one, L minus, L into
L minus x.
L minus x, right?
Yeah.
Got it? So most of these problems regarding the capacitors, since the capacitance doesn't depend upon charge on the voltage, you should know the geometry. Okay? The way you know the geometry, now it will be easy since I explained. So when the questions come from the exam, you have to sketch it, okay, similar way, and you have to find the area. So if you can find the area of these capacitors, I mean for finding the capacitors, half of the problem is done, right? Unless if it is a variable capacitance like we did, as a DC is equal to, as a changing as a function of x, you have to find the y of x or distance as a function of x. But most of the problem with the discrete capacitors, you will have to find the area of each one, okay? So what is the capacitance of first one? Epsilon 0, Lx. What is the separation? D. Should be correct. And what is the second one? Epsilon 0, L into L minus x over D. Right? Correct? Perfect. That's what I was checking. So you have a K then. Now how you find the force acting on this slab? You have to add the capacitance first. Okay? So you have U of x is equal to Q squared over 2 into C, right? Or half Q squared C. For your convenience, I will write this. This is the same thing. So you just take Q squared over 2 into C1 plus C2, because the C is in parallel, right? So you can add. So you add these two here, okay? And then you find the U of x. So Q square over 2, what is C here? The first one, epsilon 0, Lx over D plus K into epsilon 0 L into L minus X over D, right? So what is this? So Q square, okay, I can take out I can take out epsilon 0 L from both of them over D, right? So 2 epsilon 0 L over D, right? What else I can take out? Nothing much, right? So this will be X
X plus K.
plus K L minus X, right? Should not get confused with this one. So this is your, you can rearrange this one in a different way. You can just write, you can, if you want, you can just, I don't care whether you rearrange it, but if you want, you can just write this one in terms of KL, because I always insist to keep the constant one side, into 1 minus K into X, right? Is it correct? Correct? So I have X here, right? And I have minus Kx here. So I took X out of this one. So 1 minus Kx will be this one, right? So now what I have to do? I have to integrate. How do I integrate this one? Sorry, not integration. So the force is mu over x. So differentiation, right? So minus of dou over dou x of whatever it is. Q square over 2 epsilon 0 L over D KL. There's a bracket here, okay? KL plus 1 minus K into X, right? So how you differentiate this function? Q square over 2 epsilon 0 L over D KL plus 1 minus K X minus 1, right? Right? So you just take the differentiation. So minus Q square 2 epsilon 0 L over D. What is the differentiation of this one? This function, differentiation. Minus 1. Right? Right? Into 1 minus K. Right? Divided by KL plus 1 minus K X square. Am I right or wrong? If you have a function like a to the power n, how you take the differentiation of this one? Or x to the power n. N into x n minus 1. Okay? So check here. My n is minus 1. So minus 1. Right? And I have a function which has to differentiate with x. Right? So that constant, whatever it is. Okay? And then my x is this one, right? So k plus 1 minus kx minus 1 minus 1. That is minus 2. I just wrote this one in the denominator. Okay? So this one I wrote. And then I can just cancel this one and this one. And you can rearrange it. So I'm writing back. You can try this yourself, okay? You have to try this yourself because there is easy way to make mistakes, and my grader will just not give you marks for all the mistakes. Yeah. Which one? This one. This one. This is in denominator, right?
Yeah, can I just take Q equals 1 and then you can bring by question?
You can do question. So it's fine. Either way you do, you will get this one. If you use the question, I just wanted to use the x power n. That's the easiest way to use. So I just wanted to make it this one. Now, let's check this force. Q square minus minus will cancel, right? 2 epsilon 0 L over D, right? Into 1 minus K over KL plus 1 minus K x squared. Okay, now just look, this is the force I'm just having when it is inserted. This is the final answer. But if I ask you as a sub question, find the force when the slab or dielectric slab is inserted half way of the capacitor, which means my x will go to L by 2. Okay? Then I can just substitute this one. X is equal to L by 2. My force will be Q squared over 2 epsilon 0 L over D, right? 1 minus K, this is K by the way, don't get mistake. Divided by K L plus 1 minus K into L by 2 square. L square I can take outside. So the final answer will be Q squared over 2 epsilon 0 L cube. Either I can just leave it D here or I can write Q square D. That depends on you. Then K plus, right? Half, right? I'm just multiplying this one. Minus K half squared. Correct? Correct? I can go on further. So this will be, my force will be Q squared over 2 epsilon 0 L cube over D, K minus K half, that will be K half, right? Plus half squared, right? So I can take out this 2 from the bracket, so that will be 4, 2 squared, right? And just cancel with this one. So the final answer will be 2Q squared over epsilon 0 L cube over D K plus 1 square. Here, there is 1 minus 1 minus. In some cases, I will ask you to prove the force acting on a dielectric slab when I insert the slab into halfway through of the capacitor, parallel plate capacitor. Find the expression for force, and I will be giving you this expression. In some cases I'll just not give you the expression. Then you can, even if you write this form, I will give you the mark. This is just a reduction of that. Okay. If I give you to prove this one, you have to go up to this one. So today I thought of giving you this as a homework, but by looking at your answers from the previous one, it seems to be difficult. But I will give a simple example as a homework.
Professor?
Yeah.
Last part there, how do you get it in that form?
This form.
Yeah.
You just have x, right?
Yeah.
Here, so you just multiply KL.
Yeah, KL.
KL you keep here. KX, right?
Yeah.
KX here. Just x.
Can't really see from that's why.
Okay, maybe you are not seeing from this one.
Yeah.
So the next question. Find the capacitance of a cylindrical capacitor. This is the last. Should I remove this one? Sorry?
Earlier when we found the total capacitance, why don't we
We don't integrate, we take differentiation. Because we found the total capacitance and then we found the energy. So when you have the energy, the force is a differentiation of the energy.
But before we put it into the energy equation, why don't we integrate capacitance? It's a function. So it should be changed.
No. The capacitance here is constant. This region is constant. It's not changing.
Yeah. But what?
This is constant.
You're putting.
When you put inside it, it will be changing. But it is a constant change. It's a constant change. It's not just not changing over the, for example, I just keep inside this. So I just leave it there. So this will have a force experience. So I just ask you to find a capacitance when I insert it. But if you keep inserting it, of course, for the region wherever it is moving, this will be changing. But this will changing in a constant manner, right? Whatever this one. It's not like the other one, like variable as a function of x. It's not. Now, I have a question. Find the capacitance of a parallel plate. Sorry, cylindrical capacitor as shown below. So I have a cylinder, right? And I have a concentric cylinder. This problem you didn't solve, okay, by the way. I thought of giving you the other one as the class activity, but I solved it because I just wanted to finish the chapter. Okay, so I have to have a constant cylinders, and I will have the. Just give me one more minute, then I will finish it. So I have the area of the radius is A, and this one is B, and the length is L. Okay? And assume L is much more than A and B, so that consider using process. How do you find the capacitance here? So you first find the electric field, right? Then the potential, then capacitance. Okay, this is the clue. So find the electric field. You have this one, right? So you just take the Gaussian surface in between. For those who want, they can leave. Okay. So this is just an explanation. So you just take this Gaussian cylinder here in between with a radius of r, right? And electric field you find here, the electric field between A, right, R and B, right? So and electric field, you find the electric field here. Then if you have electric field, the potential will be A to B, E dot dr, right? Then you can find it. I want you to solve this problem and bring it in the next class. And this is all about the chapter 25. And if you have some interesting problem than this one, just type, you can solve in the class, next class, okay?